All right, today more inequalities, which will definitely involve triangles, but that's not how it'll be framed. Okay, so today we're going to talk about the concept of optimization. And the idea behind optimization is this. Okay, let's say that we wish to either minimize or maximize a certain quantity in accordance with given constraints. I know that that's very abstract, but that does describe what it is that we wish to do. Here's an example. We might wish to find the segment of minimum length that takes us from a point to a line. We'll actually consider that. Or perhaps the segment of maximum length that takes us from one point to another on a circle. If one is given a circle, then of course one can choose 2 points in that circle in many different ways and construct the segment between those 2 points, and it should seem obvious that you'll get segments of different lengths. And one might wish to maximize the length of that segment. That would be an example of an optimization problem. So if you lay down certain conditions, like for instance, you want to go from a point to a point in a circle, and then you wish to say that you either wish to minimize or maximize that quantity in accordance with a given constraint. This is an example of an optimization problem, okay, which obviously involves inequalities because we wish our quantity to be either the greatest or the least, depends upon the situation. Okay. So in this particular section, it will involve points and lines, and then in the next section we'll consider explicitly circles. So it'll be some of our first results about circles. So before we launch into the proofs of the results today, how does one in general prove that a certain like path from a point to a point on a circle is the optimal one? Either it's the minimum or the maximum. We'll prove that we have a maximum. Well, we prove that it's shorter or longer, as the case may be, than any other that meets the same constraint, right? So how do we prove, for instance, that a certain path, and you can probably guess which one it is, a certain path from a point to a point on a circle is the maximum distance that one can go from a point to a point on a circle? We'll prove that it's longer than any other. And the way that we typically do that is we'll consider like a representative other, and we'll show that our chosen one must be longer than that representative other, and then we will conclude that it's optimal in the sense of the greatest, and that's just how we do this. That's how we go about it. All right, so before we launch into the optimization results today about points and lines, we need a result. We need a result that I will call the unique perpendicular. We have to know that given a line and a point not on it, a unique segment exists from that point to that line that is perpendicular to the line. It's very plausible, I know, but we're system builders. We can't just say that we think that this is true. We must find a place for it in our system, and if it's provable, we should prove it, and this is absolutely provable. Okay, so here's the setup. So we've got a line A, at a point P, not on that line, and we wish to prove that a segment from P to A exists that is perpendicular to A. That is, we can draw such a segment, and we need to know that it is unique. That is, there is only one point to which we could go on A so that we get the perpendicular from P to A. So there's really this is a two-part proof, okay? We must prove existence, and then we must prove uniqueness. So the first question is, how is it that we prove existence? Okay, and there are various ways that this could be done, and I'm about to show you a way that's not Euclid's way. But I think it is fairly straightforward. So to prove existence, we'll do this, okay? We do have an allowed construction in a situation like this that we've already proven is already in our system. We already know that if we have a point P, not on a line A, then we may, through that point, construct a line that is parallel to A. So we can construct the parallel, and we know it's unique, but we don't even need to know that here. So I will let that line be called B. Sorry, I'll erase that out. So I'll let this line be called B. So I've constructed B through P so that it's parallel to line A. Okay, that's our parallel construction rule. And then here's what I wish to do. Let me use the protractor postulate so that I create through P with B a right angle. Okay, I know that I can do that. Right, so I will construct a ray through P that makes a right angle with B. That's just simply the protractor postulate that tells us that we can make an angle of that measure. And then think about the angle that ray makes with A. Okay, we have two parallel lines, and then that ray that I just constructed acts as a transversal. It intersects B, so it must also intersect A. So that ray acts as a transversal. And then we can apply one of our consequences, one of our parallel consequences, like for instance, I don't know, consecutive interior angles are supplementary. So like if we call the right angle 1 and the angle on A 2, we know that 1 and 2 must be supplementary, but an angle supplementary to a right angle is itself a right angle. So that ray, of course, must make a right angle with A as well. So we now know that it is possible to construct the perpendicular from P to A. We know that that can be done, but we haven't yet proven that that perpendicular is unique. Okay, and how do we prove that it's unique? Well, this is very typical of the kind of work that we do. We assume that there could be another, okay, and then rule that out. So what would another look like? Another would look something like this. Okay, so if we were to assume that there could be another perpendicular from P to the line A that would go to a point R, distinct from Q, then we would have a situation like this. And it should be clear that for various reasons this is impossible. We would, for instance, have a triangle PQR that has two right angles, which means the sum of its angles exceeds 180, which is impossible. Also, it would have to follow that line PR is parallel to line PQ because they both make a right angle with A, but those lines are not parallel because they intersect at P, so this is certainly impossible. Okay, so here's what we know then. There does exist a perpendicular from the point P to the line A, and that perpendicular is unique. Okay, now let's talk about distance a little bit. Okay, this will be the language that we use to sort of frame our optimization problems here. When I use the word distance, of course, this will be the distance from one object to another, whatever they are. I mean the length of the shortest segment that connects a point on one to a point on the other. Okay, so whatever they are, so like a triangle here and a triangle over there. Imagine that I choose a point on one, a point on the other, and I construct the line segments, and I choose various points to do this. The distance is the shortest of these line segments. Okay, so distance by definition is an optimal quantity. It's the shortest. So distance from point to point is just then by definition the line segment that connects them, okay? Because there's only one way to choose a point from point A and only one way to choose a point from point B. Each is just the single point. So there's just one line segment here, so it must be the shortest. There is no other segment from A to B that could be longer. So the distance from A to B is just by definition of distance, the line segment. But now let us consider the question of the distance from point to line. Okay, I wish to go from a point to a line, and this will mean that I traverse a line segment from P in this case to some point on M, and I wish to have the distance. Okay, that is, I wish to have the shortest of all possible segments that go from P to a point on M. My contention is that the shortest of all of these segments is the one that makes the right angle with M, and we know that that is unique. Okay, that's the unique perpendicular, which we proved just a moment ago. So how does one prove this? Well, as I said a moment ago, it's a kind of comparison proof, right? One compares the length of the perpendicular to the length of any other segment, which will be a non-perpendicular because the perpendicular is unique. And that's what PR is in this case. PR is a representative non-perpendicular segment from P to M. And so what we need to do is to compare PQ to PR. Notice, of course, that what we have is the right triangle PQR. And let's see, here's something we know, right? And this actually came up on one of your problem sets. In a right triangle, the hypotenuse must be the greatest side. Why is that? Because it's opposite the greatest angle. That's the converse of the anisosceles triangle theorem. So this is something we immediately know. So we conclude then that the distance from a point to a line is the length of the segment from the point to the line perpendicular to the line. Now, the final question we wish to consider is distance from line to line. Okay, and we have two possibilities here. Okay, either our lines intersect or they do not. Okay, if they intersect, then the distance between the two lines is 0. Okay, what's the shortest line segment that connects a point on one to a point on the other? Well, choose the point of intersection. okay? That's the distance of 0. One can be at a point on one and also simultaneously be at a point on the other because they intersect. So the distance between them is 0. So that's trivial. But what about parallels? What's the distance between them? I claim that the distance is given by the length of a segment from the first to the second, perpendicular to them, okay? I say perpendicular to the second, but of course, if it's perpendicular to one, it's perpendicular to the other. I say that the perpendicular, okay, segment from one line to a second parallel line, that gives the length. All right, so there's an illustration of that. And the proof has to be two-part, okay? I didn't say which perpendicular, okay? Obviously, there'll be multiple perpendiculars for one of a pair of parallel lines to another. So what we must prove, first of all, is that the lengths of all of those perpendiculars are the same. And then we must prove that the length of any of those perpendiculars is shorter than the length of any non-perpendicular. Okay? So, part 1, okay? Let us first of all prove that if we have two parallel lines, M and N in this case, and if we have one perpendicular, PQ, and then a second perpendicular, RS, that those must be equal, okay? That is, the length of any perpendicular from one of a pair of parallel lines to the other is equal to any other perpendicular from one to the other. Well, this is really fairly trivial given some of the results that I've had you prove about quadrilaterals. If you were to consider, I don't know, let's name some angles 1 and 2 and 3 and 4. Our lines are parallel. I'll mark that. So our lines are parallel. So by the consecutive interior angles consequence, 1 and 3 are supplementary, which means that 3 is a right angle. And for a similar reason, 4 must be a right angle. And then consider the kind of quadrilateral that PQSR has to be. It has 4 right angles. You know, it's a rectangle, right? And as we discovered, a rectangle is a variety of parallelogram, and parallelograms have equal opposite sides. So PQ has to equal RS. It's really fairly easy. And now the second part, okay? So we know that all those perpendiculars that like join a pair of parallel lines are equal in length. We need to now prove that any of those perpendiculars, which are all equal in length, is shorter than any non-perpendicular, okay? And how do we prove that? Well, we have a representative non-perpendicular, which is xy, and we'll prove that our perpendicular is shorter than that. So we have to prove in this diagram that PQ is less than xy, where of course we're given once again that M and N are parallel. How do we do this? Well, we know that from a point, not on a line, and x is not on n, there does exist a unique perpendicular from x to a point on n, which I will say goes to a point. Perhaps I haven't used z. Okay, so we'll call that point z. So there's our unique perpendicular construction that we discussed a moment ago. And then consider part 1. Okay, part 1 tells us that PQ and XZ must be equal. And then now consider XZ and XY. Well, again, we have a right triangle, XZY. XY is the hypotenuse, XZ is the leg. As we have proven in a previous problem set, the leg is always less than the hypotenuse. So XZ is less than XY, but XZ is equal to PQ, so PQ is less than XY. And that's your proof. That's how it goes. So here's what we've really proven then. We've proven that all perpendiculars that join a pair of parallel lines are equal in length. We've also proven that each perpendicular that joins a pair of parallel lines is shorter than any non-perpendicular that joins those lines. Thus, we may conclude that the distance between a pair of parallel lines is the length of any perpendicular from one to the other. Or if you like, this is the way it often gets put, and students often put it this way independently, parallel lines are everywhere equidistant, and the distance between them is the length of a segment from one to the other perpendicular to each.